Okay, so let's continue our discussion of negation of quantified statement. Let's first look at one example. Suppose I have a statement of the form for all x in D, px, where p is a predicate. So if we have such a statement, what will be, note that this is a quantified statement. What is negation of such a statement? So it's not hard to see that negation of this quantified statement is there exists an x in D such that not px. Okay, let me show you an example. Suppose we look at example is this: all FIU student has a Panther ID. And the negation of such statement, of this quantified statement, will be the opposite of this one. And therefore, the negation of this, what it is? The negation is there exists a student of FIU who doesn't have a Panther ID. Okay, let's look at the second example, second type of negation. If my quantified statement is there exists an x in D such that qx, let's look at what will be the negation of such quantified statement. So this is saying that there exists an x such that qx is true. So negation will be for all x in D, qx is not true, right? So the negation of such a quantified statement is for all x in D, not qx. The simple example is if I have a statement like there is a student in my class failed last year. If someone claimed that there was a student in my class failed last year, I want to say what he said is wrong. Then what I really want to say is all students in my class passed last year. By the way, I hope this is true for this class. Okay, the third kind of negation is implication. For all x in D, px implies qx. So for such statement, what would be the negation of such statement? Okay, let's see what does it mean. Remember this implication P, if Px then Qx, we can write as negation for all x in D, either not Px or Qx. Okay, if we write the implication in this form, then it should be clear, because then we can apply the Morgan's law to negate this statement, and therefore we use our first one, apply this first one. So the negation is there exists an x in D such that the negation of this not Px or Qx, and which is equivalent to there exists x in D such that applying the Morgan's law, okay, this is our theoretical deduction of this logic form. Let's see it makes sense. So let's see example. My example is my statement is all student that are good at math must be good at programming. So it's easy to see that student for all x in D, x is here a student, right? And what is P? P is good at math. And what is Q? And Q is good at programming. So in order to refute this, you want to say the opposite. Of this statement. Programming. If I want to negate this statement, what should I say? You want to show an example that student is not satisfying this claim, that not satisfying this implication. In other words, you want to demonstrate by a student who is good at math, but not at programming, good at programming. And therefore, this, I mean, intuitively should have the negation should be there exists a student. And such that, sorry, let's say, because we want to, there exists student, let's say X, such that X is good at math, but, or equivalent to say, and X is not good at programming. Which is exactly, there exists X in D such that PX and not QX. PX is good at math and not QX is not good at programming. Okay, let's move on to next page. So the next type of negation we are going to look at is the existential quantifier. There exists X in D such that PX and implies QX. And it's easy to see that this is equivalent to say for all X in D, of course, using De Morgan's law, and the PX and not QX. Let's see example of this such a quantified negation of a quantified statement. The original statement is there's a student admitted to FIU, but doesn't get a Panther ID. So you want to say, you want to negate this statement, and what you want to say is for all students admitted. Okay, so sorry, here P, what is P? P is admitted to FIU, and the Q, sorry, P here, and the Q is not getting a Panther ID. Therefore, the negation should be all students admitted to FIU get their Panther IDs. Okay. So next, I'm going to make a few more remarks. So I want to say what is the relations between among for all there exists and all. If you look at this example more carefully, you may notice that the similarity between negation of a quantified statement and De Morgan's law. Okay, why that? I think you can see this is because of a very simple reason. Let's say, for argument's sake, let's say very simple case that D just consists of 3 elements: x1. The pen is not working very well. x2, x3. Okay, of course D can be an infinite set, but let's, for argument's sake, we assume that very simple case, D is just consists of 3 elements. And then what is our statement for all x in D, Px? And in this simple case, we know that this is nothing but Px1 and Px2 and Px3, right? We just say, okay, Px1 is true, Px2 is true, and Px3 is true. And what is the negation of this such statement? By the way, it's very easy to see that De Morgan's law not only apply to you have 2 predicate, you have and of 2 predicate. It can be applied, can be generalized to any number of predicate. And what I'm saying is, if you have this x1 and x2 and xk, and if you want to know the negation of this, and you can, it's not very hard to show that, but and also we are going to learn how to show this later in this course. And this is equivalent to not x1, or not x2, or, and so on, or x, not xk. That what I'm saying is De Morgan's law can generalize from end of two predicate to end of arbitrary number of predicate, and the same thing for all of predicate, negation of all predicate. So in our case, we only need to worry about 3 predicate. And so if you trust me, De Morgan's law tell us this is not x1, or not x2, px2, or not px3. What does this mean? If you think about this negation of px1 and negation of px2, negation of p as a new predicate, then what is this saying is just there exists x such that not px. So therefore, this explains why we have this the negation of universal quantifier will become the negation of universal quantifier will become an existential quantifier of the negation of the original predicate. And similarly, if we say there exists x in the qx, okay, this is just nothing but qx1 or qx2 or qx3. And now if you want to negate this statement, you negate this statement, right? And what you get is by De Morgan's law, you get not qx1 and not qx2 and not qx3. Of course, this is equivalent to say for all x in D, not qx. Okay, I hope this explain the relation between this existential the relation between when you negate the existential quantifier, you get a universal quantified statement, and then when you negate the universal quantified statement, you get an existential quantified statement. Okay. Let's move to next page. So we're going to talk about something called vacuous true. Of universal. So consider the following statement. P. So all humans living on Mars don't know how to count. My question is, it is true? Is P true or false? The difficulty is we know there are no human being living in Mars. living on Mars. So how can I know this is true or false? One way of seeing our convention of such statement, because this is the statement is called vacuous truth of universal statement. We claim that our convention, all you can say that you can think about is our convention is for such statement, we always take it to be true. So one way of seeing the reason behind this is we just look at the negation of P. If we know the negation of P is true, we know that the original P is false. If we know the negation of false, then the original statement should be true. So negation, what is negation? Negation is there is a person, there is a human living on Mars who doesn't, who know how to count. And this statement clearly is false because you're claiming that there is a person living on Mars and he know how to count. And I definitely don't believe you because I know there are no person living on Mars. So this is definitely true. I'm sorry, definitely false. This is false because it's easy to argue that this is false, and therefore we can assume that this is true. And in general, we always take we call a statement X in D sorry, we say the following statement: for all X in D, if Px, then Qx. We call such statement is called vacuously true. Or true by default. If X in D such that Px hold is the empty set, the empty set. That is, no X make Px to be true. In this example, in the example we demonstrated before, in this example, Px is living on Mars. X is human being. So we know that there are no human living on Mars, and therefore this set is the empty set. And we use the convention that for such implication, it's always true. Okay. So the next topic we are going to discuss is variance of universal quantified, universal conditional statement. So recall that for this if P then Q, this conditional statement of P implies Q. We have converse, inverse, and contrapositive form. And such term can also be extended to universal conditional. So this suppose the statement is, okay, you want to universal conditional statement. So we want to generalize this conditional statement to universal conditional statement. Okay. Suppose the statement is for all x in D, and we are going to. I'm going to discuss briefly why we don't care about existential conditional statement. So for existential conditional statement, we don't have too much interest. For all x in D, if px, then qx. So this is our original universal conditional statement. And what is the contrapositive? And the same thing, we just remember this is for a universal quantified statement saying that there's a P implies Q hold for every X. Okay, so the contrapositive is nothing but for all X in D, and not Q implies if not Q. Sorry, we shouldn't forget about this X. If not QX, then not PX. And what about the converse? The converse is for all X in D, if QX, then PX. And what about the inverse? The same thing for all X in D, if not PX, then not QX. Okay, I think this there's nothing to say about this. If you know how to transform the regional conditional statement into its contrapositive, converse, and the inverse, you should have no difficulty in transforming a universal conditional statement into its contrapositive, converse, and the inverse. So let me briefly discuss why we don't care about the existential conditional statement. Because for universal conditional statement, so we have this for all x, if px imply then qx. So what is this is saying that the true set of dp is a subset of dq. That means that such statement is actually a set relation. It's a set property. But the existential conditional statement don't have such a nice and useful set inclusion property, so we don't care too much. Because universal conditional statement is very contain a lot of information. It's a very powerful statement. It's a very strong statement, but existential conditional statement is not as powerful as a universal conditional statement. Okay, let's see examples to how to do this transformation. The example is the statement is for all x in R, if x is bigger than 2, then x squared is at least 4. Of course, we know this this statement is true. So translating this into our language, so this x is bigger than 2 is our px, and x squared bigger than 4 is our qx. So what is the contrapositive? Contrapositive is for all x in R. If x squared is less than or equal to 4, then x is less than or equal to 2. Which is, we know the original statement is true, right? because if you look at this x squared, the plot of x squared, and this is 0, this is 2. Not very, didn't plot very well. So let's try again. So we should have a shape like this. Fx equals x squared. So this is x equals 2, and this is 4. So therefore, x bigger than 2 is in this region, and therefore x squared larger than 4 are definitely true. So the counterpositive is for all x squared less than 4. If x is less than 4, then x must be less than 2. So we know that okay, this is because the counterpositive original one is true, the counterpositive is also true. The second one is converse. What is converse? Converse is for all x in R, if x squared is larger than 4, then x is bigger than 2. So it is true. So if x is larger than 4, then x is bigger than 2. Clearly, this is not true, right? Because we can take x, for example, x equals -3. And we get 9 in this point. So this is not true. False. And what about the inverse? The inverse is for all x in R. If x is less than or equal to 2, then x squared is less than or equal to 4, which is also false, because -3 is less. If we take x equals -3, then x is less than 2, but x squared is larger than 4. By the way, we know that the converse and the inverse, these two statements are equivalent because they are contrapositive to each other. And therefore, we know if we know that the converse is false, then the inverse must be false as well. Okay. Let's look at the next topic. The next item is necessary and condition and sufficient condition. So for all x, Rx is a sufficient condition for all Sx. And what the meaning of this? This means for all x, if Rx, then Sx. Okay, this we have seen this before, but not in the quantified statement. What about, this is a sufficient condition, and what about the necessary condition? The necessary condition is for all x, Rx is a necessary condition. For Sx, and this is equivalent to say that for all x, if not Rx, then not Sx, and which is equivalent to say for all x by the counterpositive, taking counterpositive for all x, if xx, then Rx. Okay, sufficient condition means this direction, from left to right, and the necessary condition means from right to left. Okay. And what about only if? For all x, Rx only if Sx. So the meaning of this is it means for all x, if we have not Sx, if not our Sx, then not Rx, and which is equivalent to say, save some space. Means for all x, if Rx, then Sx. And therefore, we somehow say that Rx, if and only if Sx, which means Rx only if Sx means Rx implies Rx, Rx implies Sx, and if Sx, Rx if Sx means Sx implies Rx, and that means we have this Rx and is equivalent to Sx. And therefore, we sometimes use if and only if to denote equivalency, that the two conditions are equivalent. Okay, let's see an example. Sorry, I think I need to go to next page anyway. So the example is let's try to rewrite the following statement. Using quantified conditional statement. Sorry, not using as quantified statement, as quantified conditional statement. The first one is squareness is sufficient, is a sufficient condition. For rectangularity. which is definitely true. That means the shape is a square. Then that means implies that the shape is rectangular. And the second one, but we want to translate into logic language. The second example is being at least 35. I'm not sure, but I think this is the requirement of the Constitution, United States Constitution. Being at least 35 years old is necessary. It's very important. It is not a sufficient condition. Otherwise, we would have a 300 million U.S. president. This is only a necessary condition to be elected as the president of the United States. Okay, so what's our solution? The first one is we want to write this as a quantified statement. The first one is for all shapes. If it's a square, if it is a square, this is a universal quantified condition. If it's a square, then it is sorry, it is a square. It is a square. That is then it is rectangular. Or you can say that it is square. If it is square, then it is rectangular. Anyway, so this is part A. And what about part B? Part B is we want to say that for any elected statement, United president, his age is at least 35. Right, for every. And for every means it's equivalent to say for all. So therefore we can say for all elected, let's to be more precise, for all US president US president what should I say? No, sorry, I think it's better to not write this way because I want to use a universal quantified statement. So I want to say for all people in the world. If he or she is elected as the president of US, then he or she is at least 35 years old. More precisely, at the time when elected. Because this statement is only required to be at the moment of being elected. Okay, I think I'm going to stop here for this video.